Hi, my name is Tiago. I'm from the design department from the University of Brasilia, Brazil. I'm here to present the paper Species in Morphogenesis, introducing symbiogenesis as an additional method for the evolutionary process of a network. It is co-authored by the professor researcher Marilia Bergamo from the Federal University of Minas Gerais. But before we start to talk about this symbiogenesis inspiration, first we have to talk a little bit about the original system, morphogenesis. Well, it was created to discuss the use of genetic algorithms for the development of systems with greater level of emergency. So we did that because Galanter said that there is a difference between the level of complexity existing in nature when compared to the computational systems created by artists nowadays. So he did this approach inspired by the Gelman's definition of effective complexity. That is a length of a brief description of the system irregularities. So it's situated between order and disorder. It's a little bit of both, guided by some kind of proficiency. And by that, we understand that it could be compared to the concept of organized complexity suggested by Dawkins, where the living things are complex systems as well. So we inspire the system on the Dawkins biomorphs, where you can navigate through the genetic space of the creatures, and also the Conway's game of life, because you have these rules of proximity to define if the agents live or die. We for sure inspire ourselves on the first computational artists. They try to express the behavior of some algorithms so people could feel it. And we try to do that, but in this case, we're trying to express the evolutionary process. There's a lot of other systems that are relevant to us, but we don't have time for this right now. So this system, morphogenesis, is a tribute to Turing, where we try to create this microscopic universe where you have these fundamentals of language, like lines and shapes, that are fighting as cells to define some picture in a big context. That's the metaphor here. And this system was created as we call a creative heuristic process of experimentation. And by that, I mean, I have to admit that as a designer and that study psychology, I am not a developer. And it was just a trial and error approach where we try to be faithful to the concepts, and we did not use any other API or no algorithm that was there. We just built it from the scratch, and we created this multi-agent complex adaptive system with genetic algorithms. We use processing to do it all. So as the environment has only those agents, the agents are this small lines. The body are this small lines like a scribble that tends to keep its shape in the long run like a signature. So we have these geometric shapes on their bodies. The head is the bigger one, so we have a square head here. This square head is not friends from the other one because it's a circle head. So they consider themselves the same species when the shape is the same or very near their own shape. They have some colors to give some identity, some variability. They die and lose those colors. They become gray, stop moving. But when they're alive, they move and stretch their bodies. They create these small sounds like traffic, like when you have this one instrument and an octave to express themselves. They can see each other. They can chase or escape from each other. They can create also collaborative groups to help each other survive or to fight together. They also have this situation with submission, where one agent is able to hook another agent with the line of its body, and it drains its energy in this situation. But they also ovulate, they get excited, they mate, they give birth to another creature. and this creature, it has the combined DNA from their parents. They fight when they're not friends. This big square here is a fighting, and this circle is a mating, and they feed from the dead bodies of their foes to feed themselves. Well, they have this initial random behavior, like a Brownian motion, and when they want to do something, like search for food or chase a weak foe, we just weight this probability. We have this kind of state machine inside them, but we don't use categories. It's more like a big sum of a continuum variable. So to exemplify some interactions, we have this sequence diagram here, where agent A sees agent B, and it tries to evaluate if they are the same species or not. They think that they're not from the same species. So agent A thinks, yeah, I'm gonna move away because I think it is stronger than me. And by doing that, it goes to near agent C, where it can see agent C and evaluate again, are we from the same species? And in this case, it thinks that, yeah. So it tries to evaluate if it's mature enough to mate, and it thinks that, yeah, so it tries to move forward to hang out and stay near the other agent. So when we run the system for the first time, we have these random agents with random numbers to all their variables. So we have this probable situation here, where you have the agents spread on the environment with different colors. But as the rules apply and we start to evolve the system with those rules I presented you, it starts to change. They start to move and they start to evolve. They die and they give birth to other creatures, and we start to see a different compositions. So to exemplify that, I have a short video here where you can see it's accelerated video. There's no sound this time. You can see they are moving around, creating groups, and sometimes they create this big group like swarm intelligence. They start to walk together and fight together as one, but sometimes they just spread and becomes two other groups. So it's what happens in time with the system. You can see this big group here moving around like a collective creature that just split itself. Well, I have here also the system running. I'm going to show you. This is the system running. It's not a situation with great equilibrium. I'm going to turn the sound on. It's a bit noisy. It's a bit loud, so I apologize for that. So this is what happens within the system. Well, with that behavior, we have this kind of compositions like this one or like this one, where we can see these creatures as, I don't know, seaweeds or fungus or something like that. This. And we have some emergent behaviors as well, where you have some colonies or some aggressive behaviors like predators starting to show in the system. And we have also some navigation through the genetic space of the creatures. In this case, they're like small frogs that stays in the same place to keep their energy. And then they just start to jump around and go to the place they want to go. But well, what matters to us is that when you start the system, you have this random expected behavior. And when we have some composition after a few generations, like, I don't know, 300 generations, we have these different compositions. We are interested in understand how it feels, this different situation, because the use of genetic algorithms focus on a fitness function that defines what you're aiming for. And in this case, we try a different approach where they just have to be alive. We don't stop the system to select or choose which ones are the best. They don't even know which ones are the best. So the ones that are still alive create the composition, and they don't know how to what to choose if they don't try explicitly to keep their own energy. So that's the indirect evolution we are trying to understand. And it's a little bit more than that. We have this situation where the agents are blind to the colors, and they're deaf to the sounds. So we create this big engine that simulates the evolutionary process. And we try to create some variables that we could perceive in one side and see what happens, what we get from the other side, if there's a little bit of emergence here. So we get the system to some exhibitions. We try this multi-touch screen so people can interact with agents like fishes on a water, where you touch the water, they move away, or if you just touch them, they don't like it. But people start they like the system, you understand this complex behavior, but they don't understand how it becomes a composition. So we try another setting where it's like a game. We suggested a game where you have to pay attention to one creature, but we aim to provoke people so they understand the short lifespan of a creature, so they understand that the composition is a result of new birth and the death of the agents. So they understand what is happening and how evolution is shaping the arrangement. So we also made this small empirical qualitative study where we try to understand what's the perceived intentionality from these compositions, if they're made by a computer or by human, and the aesthetic evaluation of the public as well. And we try to understand if it's somehow related to effective complexity. And our preliminary results suggest that maybe we have some kind of intention here, where you compare the random agents. The first time someone sees the random configuration, they kind of have some curiosity, some interest, but just as soon as they see the second or the third arrangement, they say, okay, is another one of those. They mean nothing to them. But when you have some output of the evolutionary process, there's some curiosity. And so we understand that it seems that the use of these evolutionary techniques, they were able to trigger the interest of the public somehow. And maybe we tend to have this innate curiosity for this kind of complexity. Maybe Schrödinger was right, and we are in a search for this energy quality to sustain our life and drive us apart from entropy. Well, so this creates some intricate relations in the role of arts in relation to science, where we try to use these scientific concepts and create some work of art to express them, so people can feel them in a different way. They understand it when they're in school, and it corroborates another of Galanter's statement, where we could just create some good hypothesis for testing later, when we have this specialization in try to understand what people feel and how could we research and experiment what people feel. But nevertheless, this gradual evolution of the system, because it was inspired by the modern synthesis, it became predictable regarding the pacing and the time of the transformations. So here comes the Symbiogenesis approach, where evolution occurs with the establishment of mutual interactions involving physical association between individuals of different species. And with that, according to Margulis, there's a combination of different genomes that form a symbiotic consortium as a single entity. So we have another sequence diagram here to exemplify, where agent A, this time, it collides with agent B, and it stucks in the line of agent B. And in this moment, we have this highly improbable event that, if triggered, they absorb the other agent. So we have a consortium that it's not agent A or agent B anymore. It's agent E plus B. It's a new creature. Just to show you how it works in the system, we have here that submission situation I showed you before, where this triangle head here is being, it has his life being drawn. And if the event triggers, it becomes just a limp of the other agent. In this case, it loses its original colors and becomes just a limp of the other agent. And this new agent, a consortium that have some benefits, a little bit of more energy because they're working together now as one, it becomes from another species. We sum the number of sides of the geometric shapes of the heads. So we have this other creature. And in this situation, there's a new creature being born. So they are able to reproduce, but with another species, not the old ones. So here we have an example of a consortium being created. The colors of the main agent are spread into the new limbs. And here we have this colony here, and we have, it's not so good to see right now, but you have this symbiotic agent here, and we have another ones that may be able to mate with this one. So this probably will become the beginning of a new colony, and these two big colonies will co-evolve in this environment. Here we have another situation where the symbiont becomes a predator and specializes as a predator, and the colony co-emerge, where you have this low energy creatures co-evolving and fighting together, and the predator starts to hunt the weak ones and eat and feed from these weak ones. So they co-evolve, specializing as colony and as predator because of the presence of each other, like an action. Here, just to try to exemplify the effects on the system, we have this graph. It's a graph of the frequency of living agents per species. So we have here just 3 species right now. It's just a picture from the system. Like we have this, we take one picture at 2000 frames. We have 50 situations. And in this case, we don't have mutation or symbiogenesis. And what happens is that you have a big, great colony that takes place and be there forever, okay? So that's what happens. We lose some kind of variability because the system is very limited. And when we use the 1% of mutation for the DNA recombination, we get this spacing. We have this alternation of the big colonies we are showing you here. So in this case, we have this effect inspired by gradual evolution, by the modern synthesis. And when we put this symbiogenic approach, we have more dynamics. This is just an example. So we have some kind of diversity because we have the focus on one single agent that is stronger than the others. And we have these big leaps in the evolution where it creates different situations. And that's what we wanted for the system. We have, before that, we have just these collaborative groups as the strongest structures in the system. And now we have the symbionts that specialize as predators, or we have these colony thrusters occupying a leading role in the formation of these distinct colonies. And what matters to us in this case is that we are allowing the strengthening of individual narratives. We create different experiences for the public. Now you can have different situations. You can focus in one creature that we are trying to do that with that gaming approach that didn't work so well. Now you can have one agent that lives a bit longer than the others because it is stronger, and you can try to interact with this agent. You understand how it behaves facing the rest of the environment. So it's about the meaning of the system and how to express a situation that is very controlled, very limited, and try to bring some more variability so people can experience that. So the main goal of each of these features is to allow this aesthetic experience related to life processes. And the addition of this approach allowed the expression of these individual narratives that are relevant to the system as a work of art. We are not trying to simulate the effects of an already known concept that comes from a scientific approach. We are trying to express them to the public so they can feel this kind of thing that's really unapproachable by human senses. You can feel evolution because the way we live as a product of evolution, we cannot perceive how it works. So we are trying to create something that could show the meaning of a lifespan and the forging of a composition of that shows what happens in a long run to a population. And that's what we wanted to share with you. We hope to take this one to the public as soon as the pandemic allows us. So thank you very much. I'm loving being here. I'm really thankful for this opportunity to be here in this event. And I hope you get in touch. This is our contact. Thank you very much.